So it turns out the gravitational effects, the gravity fields will affect the rate at which clocks run. And here's a little diagram. So this is a spaceship, right? There's engines here, and these are very, very smooth engines, very little vibration, and this whole system is accelerating this way, okay? Now let's imagine that we are up here, okay? And we are watching this clock here, and this clock emits little flashes of light, okay? Little flashes that go, they shoot up there, right? Okay, when this clock ticks at the first time, right? We look at this thing, and of course it releases from here and it travels up to here. But by the time I've reached here, this position is actually moved some distance this way, right? Okay, and so I see that flash a little bit later than I would have, and that's because the ship is accelerating, right? Now understand that when I see that flash of light, of course, I see that flash of light as traveling at the speed of light. I don't see any effect like that, but I do see it a little bit later. Now imagine this is the first flash, right? The first one. Now imagine the second flash. This thing flashes a second time, right? And maybe it's flashing once every second, right? Well, the second time it flashes, since the ship is accelerating, I'm going even faster. And so instead of, maybe I'm here relative to this when it flashes the second time, since I'm going faster, I travel an even greater distance, okay, between the time the flash leaves here and by the time it reaches me, okay? I travel an even greater distance, and so I'm always seeing these flashes as taking longer than they actually are leaving this clock. If you're standing next to this clock, you might see them flashing once every second. If I'm up here, I look down at that clock, and I see this clock flashing maybe every 1.2 seconds. So this low clock here seems to run slow. Okay, now we can take the same argument. We can sit here and look up at that high clock there, and of course every time the light traveling this way has a shorter and shorter distance to travel because we're going faster and faster. So we always see this clock as running a little bit fast, right? When we're down here, that clock seems to run fast. Low clocks run slow. Okay, now this is happening on an accelerating spaceship, right? Okay, and then this is that whole thing, right? And this is of course Richard Feynman's excellent acceleration, right? Okay, so if acceleration causes this, right, then gravity must cause this. If we're near a massive object like the Earth, that's what this picture is supposed to show, right? Okay, if we're on a ship like that, if acceleration can cause these clocks to run at different rates, then gravity must do this, right? And this is, of course, true. This is one of the things that we do in general relativity, right? So gravity affects the rate at which clocks run. High clocks run fast. Low clocks run slow. That's how you remember it, okay? So if we recall, there was this twin paradox, right? Where, twin A stayed on Earth and the other twin flew at close to the speed of light to this planet and then flew back, right? And we were amazed that the two twins were different ages when they got back together. But remember that these frames of reference were not equivalent, and the fact that one of the twins accelerated and the other one did not, accelerating to begin the trip, decelerating to stop, accelerating to begin, decelerating to stop, those decelerations messed with the clocks. So this is how you resolve the twin paradox. Okay, the twin who goes there and back, that's not an inertial frame. Special relativity is not expected to work, right? The flying in a circle paradox, this is kind of a fun one, right? Let's imagine that you're standing here, you're twin A, right? Twin B sits there and goes in a circle, right? And they're flying like this, and they're going 0.99 c, right? Around and around and around they go, right? And never mind the g-force, right? Well, no, do mind the g-force, right? Because see, what's going to happen here is that it's going to feel like if B is sitting there, B is going to feel like there's an enormous g-force this way, right? And in fact, from the perspective of A, B is at the bottom because of that acceleration, right? Is at the bottom of like a tower. And this would, of course, be for any radius, 0.99 c here, for almost any normal radius where we could observe this, it would be a tremendous acceleration. So the centripetal acceleration would cause this clock to run slower, and it really would run slower. You'd sit here, if they're going 0.99 c, that clock would hardly tick. Take a long time for that to tick as it went around and around, and that's because of the acceleration. There's a centripetal acceleration, v squared over r, right? And then the final thing is that, and this is something that we notice, is that radiation from quasars is red shifted, Okay, what this means, what redshift means is that remember the energy of a photon is HF, right? Redshift means that the frequency is shifted lower, okay? Okay, so the frequency is shifted lower, okay? And the reason it's shifted lower is, of course, it's, here's this quasar, here's the gravity well like this. Okay, those, whoops, went back down. Okay, those photons are trying to escape from here, right? Okay, and as they climb out of that gravitational well, they lose energy. Well, the only way they lose energy is that they lose frequency, right? Energy is HF, and so as the frequency goes down, the energy goes down. And it goes down because it's got to climb out of that well. So we can see the same spectral lines that we see in hydrogen, only they're all shifted toward the red end of the spectrum because they're near a quasar. We can see hydrogen, but it acts slower near a quasar. We actually see this. We can look across space and we can see hydrogen vibrating more slowly than it should because of the gravitational field that it's in. This is an approximate formula for this, and then it's like, where would we get this? Well, is this maybe the energy? This is the change in energy of a photon over the original energy of the photon. Are we maybe missing an M here? So are we saying that the change in energy of the photon is to the original energy of the photon as the change in regular potential energy is to the total energy of the object? Maybe that's what it is, right? Okay. Now keep in mind that near a singularity, of course, G is changing rapidly. So this is differentially true, right? We need to use, this is small changes of height. We can do this, okay? This is what everything is. So that's the change in frequency. And that's, of course, one of the things that people mess up, right? You got to use the change in frequency. F is the original frequency. G is the gravitational field strength. Delta H is the change in height. And then, of course, C is the speed of light. Write those down. Meters per second squared. Whoops, meters per second. 3.00 times 10 to the 8th. All right, I don't know why I just wrote that. I think you already knew that. So put this one in your notes. Here's a puzzler for you. Okay, a radio station at the bottom of a building. And let's just assume we're on Earth, right? Right, so G is equal to 9.81 newtons per kilogram, right? So what is the change in frequency from the bottom to the top? Okay, so we are on the top of the tower. Let's imagine. Let's just imagine that we are up here, right? And this radio station's down here. So there it is. And this is 320 meters. Okay, so what we're going to do is we're going to go change in frequency is to the original frequency, which is, of course, 93.4 times 10 to the 6th hertz, right? And then that's going to be G delta H, right? So 9.81 delta H is 320, right? And then we got to, don't forget to divide by the speed of light squared. And of course, this is an absurd problem, right? Because on Earth, we don't really notice this. And this is, of course, why. So let's do our calculations here. So 9.81 times 320 divided by 3e8 squared. That's like a really small number, okay? And then I'm going to multiply that by 93.4 e6. And I get 3.3 times 10 to the minus 6th hertz. Right? Now, because I'm up here and I'm looking down at the radio station at the bottom, it's going to be lower, right? Because remember, low clocks run slower. Low is slow. Low is slow. Alrighty. Yeah. So the answer is really, not, basically the same frequency, right? There's another example, though. The next example, if you look at it, is one where, we jack up the G force so that there is a significant thing. So look at that one, too.